Hey everyone, welcome back to the channel The Univ Sine Theta. Take a look at the medium through which we are interacting right now. Do you think it's just a device making this interaction possible? Not really, right? There's so much happening behind the scenes. Communication protocols like Wi Fi and Ethernet, data constantly being transferred, hardware built from dozens of different materials, operating systems managing every process inside your device, and of course, software platforms like YouTube bringing all of this together. Absolutely amazing when you think about it. So many technologies have to work in sync just for us to interact through a screen. But today, let's zoom in on one tiny piece of this enormous system. Something that exists in billions inside your device is measured in nanometers, switches billions of times every second, and is probably one of the greatest inventions in human history. The transistor. But the transistor inside your phone or laptop today barely resembles the first transistor invented back in 1947. So, today, as a part of our series exploring the world of integrated circuits, we are going back in time to look at the evolution of transistors from the first point contact transistor to modern nanoscale technologies, different types that shaped computing, and even the possible technologies that could define the future. So, let's get going. We've already looked at what transistors are, why silicon became dominant, how MOSFETs operate, and the physics behind them in the previous videos. So, in this video, instead of revisiting all of that, let's travel through time and watch how transistors themselves evolved. Because the transistor you have inside your phone today is the result of almost 100 years of innovation. Interestingly, the story of transistors actually started much earlier than most of us think. Back in 1920s, physicist Julius Edgar Leland proposed and patented the concept of field effect transistors. But the idea could not turn into reality due to limitation in materials, semiconductor understanding, and manufacturing technologies. The journey then truly starts in 1947 at Bell Labs with the first successful transistor ever demonstrated, the point contact transistor, built using germanium, not silicon. It was designed as a replacement for bulky vacuum tubes and marked the beginning of the semiconductor era. Soon after, in the early 1950s, the junction transistor, which later evolved into bipolar junction transistor BJT, became the standard because it was more reliable and easier to manufacture. This family continued growing into NPN PNP transistors, Darlington pairs for higher gain, heterojunction BJTs for high speed communication systems, and IGBTs for motor control applications. But even while all of this was happening, another fascinating idea was also being explored: field control devices, where instead of using current to control current, an electric field created by an applied voltage controls how charges move through the semiconductor. This idea later evolved into what we now know as field effect transistors or FETs. In 1953, the JFET junction field effect transistor appeared based on this principle. Then came one of the biggest revolutions in semiconductor history. In 1959, Bell Labs introduced the MOSFET, metal oxide semiconductor field effect transistor. From there, an entirely new family tree started emerging: PMOS and NMOS logic families, eventually leading to CMOS, combining NMOS and PMOS transistors in a complementary way, which later became the backbone of almost every modern IC. But wait a second, just combining two transistor types should not automatically make a circuit power efficient, right? Think about it. Here's a hint: they take turns rather than speaking at the same time. Then, in 1980s came BiCMOS, combining BJT speed with CMOS efficiency. As the demand for faster, smaller, and more efficient devices kept increasing, newer structures like MOSFETs, HEMTs for high frequency and RF applications, FinFETs, gate-all-around transistors, nanosheets, nanowires, tunnel FETs, spin FETs started appearing. And researchers are exploring carbon nanotubes, graphene, ferroelectric, quantum, optical, neuromorphic, single electron, memristive transistors, trying to go beyond silicon. And there is this confusion with transistor types and process technologies. Even I used to struggle to distinguish them clearly. It is more like transistor architectures evolved from planar MOSFETs to FinFETs, then to gate-all-around, nanosheet, and nanowire structures. Fabrication technologies introduced approaches like CMOS, silicon on insulator, fully depleted silicon on insulator, bi-CMOS, silicon germanium, and bulk CMOS. Different process variants also emerged. LP for low power, LP plus for low power plus, HP for high performance, HPM for high performance mobile, HPC for high performance computing, ULP for ultra low power. Memory technologies also evolved alongside them with embedded SRAM, eMRAM, and embedded flash. And here's something to be noted. While the names changed, the goal mostly remained the same. Improve speed, reduce power, reduce leakage, and fit more transistors into a smaller area. But again, all of these technologies work only if they can survive in the market. Now, let's connect this evolution with something we hear all the time. Oh, we worked on 180 nano. We taped out a 65 nanometer design. This processor is built on 7 nano. That phone comes with 3 nanometer technology. It almost sounds like semiconductor companies are competing in a race where the numbers keep getting smaller and smaller. But these aren't just random numbers, they represent milestones in the evolution of transistor technology, each generation pushing us towards smaller devices, higher performance, and lower power consumption. The journey roughly went from 10 micro to 2 nano as shown, though modern node names are now more of a technology label rather than a direct transition dimension. Interestingly, if you look at the historical node transitions, you'll notice a scaling factor of roughly 0.7, like 180 nanometer to 130 nanometer, 130 nanometer to 90 nanometer, etc. Why 0.7? Because shrinking both transistor dimensions by 0.7 reduces the transistor area to roughly 0.7 times 0.7, which is nearly 0.5, allowing nearly twice as many as transistor to fit in the same chip area. This scaling trend played a major role in sustaining Moore's law. And here's an important part. Not all devices need the latest node. The microcontrollers, washing machines, calculators, and many automotive controllers often still use mature nodes like 180 nano, 90 nano, or 65 nanometer because they prioritize reliability and cost over packing billions of transistors. Mobile processors, AI accelerators, and laptops use advanced FinFET and gate-all-around technologies at 7 nano, 5 nano, 3 nano, and below, where performance per watt becomes critical. The Wi-Fi chips, 5G communication systems, and RF front-end circuits use technologies like gallium arsenide, silicon germanium, gallium nitride, RF CMOS, or bi-CMOS, because high-frequency operation matters more than the transistor count. The VR headsets, gaming consoles, and GPUs rely on advanced nodes to process massive amounts of graphics data while keeping power manageable. The TVs and display drivers often use specialized technologies optimized for display control and image processing. Electrical vehicles contain hundreds or even thousands of semiconductor devices using a mix of CMOS control chips and power devices like silicon carbide and gallium nitride transistors. So, when you look around your room, almost every electronic device around you is using a different combination of transistor types and process technologies. We didn't just invent one transistor and stop there. We kept reinventing it for different purposes. And now we are entering an era where shrinking alone may not be enough anymore. The question is slowly changing from how small can we make a transistor to do we need an entirely different way of computing? Naturally, a question comes up. If older transistors were already working, why did engineers keep making them smaller? Well, shrinking wasn't just about making them tiny for the sake of it. It was to increase the transistor density while improving power performance and area while also making devices practical for real world applications. Smaller transistors consumed lower power, reduced switching delays, allowed faster operation, lowered cost per function. So, the ability to continuously increase transistor count per area while improving performance became the driving force behind transistor scaling. The whole story was not just making transistors smaller. As dimensions kept shrinking, engineers began running into physical limitations, forcing them to rethink the transistor structure. And that's where the evolution started from planar MOSFETs to FinFETs, then to gate all around transistors. And if you want to understand more about the physics behind it, challenges faced, transistor restructuring, I've explained it in the video Transistors from Vacuum Tubes to Modern MOSFETs. Link is in the description. Now comes the exciting part, the future technologies. Researchers are investigating technologies that could take computing beyond silicon MOSFETs, like carbon nanotubes offering higher carrier mobility, graphene transistors for extremely fast operations, spintronic devices to use electron spin than just its charge, quantum transistors to unlock new approaches like superconducting systems and trapped ions, neuromorphic devices to imitate human brain processing, optical computing to replace electrical signals with photons, ferroelectric transistors to reduce power consumption while retaining memory like behavior, and 3D stacked transistors to increase integration density. Now, all of this sounds exciting, and a question might come up. If these ideas seem so powerful, why haven't they already taken over? Remember, even the transistors we use every day were once experimental ideas sitting in research labs. Every technology comes with its own challenges. CNTs face alignment and manufacturing difficulties. Graphene lacks a natural band gap, making switching difficult. Quantum systems suffer from noise and decoherence. Spintronic devices are difficult to fabricate reliably. 3D structures introduced heat removal challenges. And in all of this, the biggest challenge would be economics, manufacturing costs, fabrication complexity, and if the technology can realistically survive the market. So, even if physics works, there's much more to making a technology successful than just theory and math. And this is what makes VLSI field feel different. We are not just dealing with code, circuits, or designs on a screen. We are dealing with something real, something that exists all around us and shapes the world we live in. And we are not just watching transistors being built. We are watching humanity push against the physical limits of matter, reinvent physics at nanoscale, and continuously find new ways to keep computing alive. And maybe someday we'll look at MOSFETs the same way we look at vacuum tubes today. Don't forget to like, share, and subscribe for more such videos. I'll be more consistent from now. See you in the next one.